Hi, Sala here. Today we are going to talk about a run-of-the-river hydroelectric power station, and I'm going to explain to you guys what it is, how it works, and some of the main features.
We can see at the top here we've got a headwater, that's the water at the higher elevation, and we've got tailwater, which is the water at the lower elevation. Now the run-of-the-river power station is slightly different to a normal power station because there is no reservoir, there's no large body of water stored. What we actually have instead of a dam is a weir. So the water runs along the river here, it comes to a weir, and then it runs over the top of the weir and continues on its journey. Now we use the weir to create a body of water at the top, and we can use this body of water to create a reliable water head or a reliable head of pressure down to the turbines. The actual name for the body of water behind the weir is called pondage. And one of the differences between this and other type of hydroelectric power stations is that the weir allows the water to flow over the top so the water flow can continue, whereas a dam stops the water flow completely and builds a reservoir. So that's one of the differences between a run-of-the-river power station and another type of hydroelectric power station which will actually use a reservoir, so a large body of water. The big benefit with a run-of-the-river power station is it's a lot easier to get permission to build a run-of-the-river power station. Obviously if you're flooding a massive valley and people have to move and there's going to be a lot of loss of life or the wildlife's going to be damaged, then people don't want that. Whereas run-the-river is relatively easy to construct and you don't have a huge impact upon nature or the people living in the area. What you might see sometimes is a fish bypass or a ladder. And what this is a means to let fish swim past or back up river, and it will usually be located just to the right in this area here or the left of the power station. So the fish will swim back up these steps or ladders and then they get around the dam and can continue further upstream. This is pretty good because this also reduces the impact of the power station on the wildlife. So let's have a quick look then from up here. We can see we've got a bit of a pedestrian walkway here. They can come and have a look at the power station, or at least the top of it. And this whole structure is reinforced concrete. The water's going to run up, it's going to reach this dammed area, it's going to flow over the top, and it's going to continue flowing down the river. We can see it's going down that way, maybe a few waterfalls and then to the lower river or the river at a lower elevation. But what we want to do is take the water before it goes down the hill, and we'll use the elevation difference or the difference in elevation to generate power. So the water is going to flow through this item here, which is called a sluice gate. The sluice gate allows us to close the inlet to the turbines, so we might have an emergency in the turbine area or in the power station, so we close this gate and that will slam shut and it will hydraulically isolate the turbines, so there'll be no more water flowing down this or in this area and down through the pipe. So we've got a grate that stops anything getting sucked into the turbines, such as large pieces of wood or plastic bags and stuff like that. And if we go, in fact what we'll do, rather than go in through the gate, I'll just spin it around here and we'll go out this way. And you can see there, I'll get out of the way of the tree. You can see the pipes coming through there, and this is known as a penstock. So this is leading down to the turbines in the power station. I'll just see if I can turn around. Okay, the pipe's running down and it's going into the power station through here. Let me just see if I can go into the power station now and show you where the pipe enters the power station. And before we go inside, let's just have a look here. You can see another valve here. This will be a ball valve, and we'll also use that to isolate the turbines in an emergency or just during general operation. So that controls a valve, quite important. And let's go now. There we go. Okay, so we're underneath the power station. What are we looking at? Inside this casing here is a Kaplan turbine. It's a vertically orientated Kaplan turbine. So the water comes in, flows in through here and into the casing. In the casing itself, if we just have a look inside, there's the vertically orientated Kaplan turbine. There will normally be inside here some sort of wicket gate which will allow you to divert water to the Kaplan turbine. A Kaplan turbine is more or less like a ship's propeller, and here you can see it's vertically orientated, it's pointing straight down. The blades here are what we call CPP or control pitch propeller. they'll adjust, and you can adjust these blades to vary the amount of power that you wish to generate. So if you want to turn the blades to what we call zero angle or zero pitch, then the water will just flow by and the Kaplan turbine won't rotate, so we won't generate any electricity. However, if we turn them to maximum pitch, or the pitch that would generate the most amount of thrust or rotation, then we can generate the maximum amount of electricity. It's pretty useful because if the valves did fail that we looked at earlier, then we could turn the blades to zero pitch and we could stop the turbine rotating. The water would continue to flow past because the valves are broken and we can't close them, or the sluice gate is broken, etc. But at least the turbine is not rotating uncontrollably. If it actually rotates uncontrollably, what it'll actually do is hit a overspeed limit and a runaway limit, and that then sends a signal to the control unit to shut the turbine down. So you want to really control the speed and do it properly. The type of turbine used here, the Kaplan turbine, is chosen because it actually works very, very well at low heads. That means the difference in elevation between the upper reservoir and the lower reservoir is very small, and the Kaplan turbine is ideal. You may even see a horizontal Kaplan turbine or a bulb turbine, maybe Francis turbine, but not as likely. And what you won't see is a Pelton turbine. If you want more information about that, just go on my YouTube channel and check one of the other videos, and you'll see we've explained what each of the turbine types do and why they're selected for each job or each application. Let's back out of there. We'll go up into the power station. In fact, let's just have a quick look at the pipe while we're there. It's got a bit of a shiny appearance, but really it'll be made out of reinforced concrete. And we can see the pipe is just flowing here and going out to, let's have a look, out into the river. So there's the pipe exiting here, and there is another sluice gate to isolate the turbines. Now if we go inside, let's have a quick look inside the power station. Inside the power station here is a generator. So the shaft comes out of the turbine, connects to a generator, and we will generate electricity. So when the turbine rotates as the water flows through the turbine, there's a common shaft to a generator, which is this item here, and the generator rotates, or more specifically the rotor rotates, and we generate electricity. And then when we've generated some electricity, we obviously need to deliver that to people's houses. And there's some cables coming out here, and this is going along there, and it'll actually go into a room which is called the switchgear room. So you can see, there you go, it's coming in through this section there, and it goes to what we call switchgear. Switchgear is used to protect the generator. It prevents any damage that may occur due to over voltage or over current. So if there's any large fluctuations in voltage in the line or current, the switchgear will open, kind of like a large switch, but it's done automatically, and this protects your generator. Remember, the generator is quite expensive. You don't want huge currents and huge voltages going to the generator. You want to protect it, and that's exactly what the switchgear here does. In addition to that, it's also very useful if you're doing maintenance on the generator to isolate it. In fact, it's not useful, it's just a requirement. You'll need to isolate the generator completely so it's safe to work on, and you will isolate it here at the switchgear. Typical voltages here for the switchgear may be 10,000 volts or 6,000 volts, for example 6 kV, 10 kV, 20 kV, and the type of switchgear used could be air insulated or vacuum insulated, or maybe SF6. At some point we'll make a video on switchgear and I'll explain to you why we use different types of switchgear and for what purposes. Let's go through the wall because that's where the cabling seems to be going. I'll spin around here and try and get a better view. Okay, so there's the cabling coming out of here, and it connects to this green item, which is a transformer. Now the green transformer is actually oil insulated or fluid insulated, and it's going to increase the voltage. Probably going to increase it to, for example, 110,000 volts. You need to increase the voltage because if you don't increase the voltage, you're going to need huge cables to transfer that amount of power. So you step up the voltage in order to reduce the current. Now there's a relationship between power, current and voltage. But imagine for a moment that in your car you've got a 24 volt cable for batteries, etc., or a 12 volt cable. These cables are actually quite thick. Now that's only for 24 or 12 volts, but the reason they're thick is because they carry a high current. So if you can step the voltage up and reduce the current, then you can have thinner cables, and this is a massive benefit if you've got hundreds of kilometers of cables. So you can have thinner cables, which means that you can save money. In addition to that, the losses that you'll have on your transfer grid or on your network will be lower if you step the voltage up. So that's exactly what we do, and that's what the transformer does. We'll step this up to, say, for example, 110,000 volts, 110 kV, and it will then go through an open air switch yard, which is this area here, and perhaps press another circuit breaker, and then it will connect to the national grid. You can see it connecting to a pole there, and that will go off into the distance, connect to another transformer to step the voltage down again, and we could use it for power in our homes, such as for the dishwasher or the microwave. So that's essentially our run of the river power station works. If you get a chance, check it out on the website. I seriously think it's worth going around the model yourself and trying to figure out how it all works and how it's all put together. If you like the video, please share it on Facebook or Twitter or any form of social media. And if you really want to help us out, please check out our Patreon page. Thanks very much for your time.